Hey everyone, welcome to our last lesson in our unit on solutions. Today we're going to be learning about colligative properties. So after today's lesson, you should be able to describe how colligative properties will affect different solutions. I think this is a pretty neat topic and pretty applicable to a lot of different things that we see in our everyday lives. A little bit of a review of electrolytes. You know, ionic compounds. And we'll find that acids and bases will do this as well. But to this point, we know that ionic compounds dissolve very well in water. And any ionic compound is considered an electrolyte because when that compound dissolves in water, it causes that resulting solution to conduct electricity because there are free moving ions in the resulting solution. Now, not everything will ionize 100% in water, but electrolytes do. And they yield ions, or they're products of that reaction that resembles a decomposition reaction. And we call this decomposition reaction, in a way, we call this dissociation. And it's a physical change, not a chemical change. And you've seen this before in a reaction, what it looks like. And I'll show you this in a second. But it's basically the ionic compound showing it dissolving in water and showing the aqueous designation as far as the phase of matter. Now, the more an ionic compound breaks up, or the more ions that compound breaks up into, it's going to affect the boiling point and the freezing point of the solution. And it's going to change the boiling point and make it higher. And it's going to change the freezing point and make it lower the more ions that we can have a solute or an ionic compound break up into. So a little bit of a review here. This is our dissociation equation. It's showing solid sodium chloride dissolving into water. So we have our aqueous designation. And we now have 1 mole of sodium ions and 1 mole of chlorine ions. So we started with 1 mole of sodium chloride in the solid form, dissolves in water, and we end up with 2 moles of dissolved ions. Remember, there's ones here. So 1 mole of sodium, 1 mole of chlorine. So we have 2 moles of dissolved ions in the resulting aqueous solution. In this example, we start with calcium bromide, 1 mole of calcium bromide solid, and it breaks up into 3 moles of ions. We have 1 mole of calcium and we have 2 moles of bromine ions. So we have a total of 3 moles of dissolved ions. This is 1 additional mole compared to the sodium chloride from the slide before. This example, we have aluminum nitrate. And again, we only have 1 mole of solid aluminum nitrate. But when that aluminum nitrate dissolves into water, we end up with, you can pause this and check your work here. We end up with 1 and 3 for a total of 4 moles of dissolved ions. Now, the greater this number gets, the more it's going to affect the freezing point and the boiling point of the resulting solution. In this one, dissolving a mole of aluminum nitrate is going to have the greatest effect on the boiling point and freezing point of the resulting solution because there are more moles dissolved into that solution. Now, a little bit about non-electrolytes. Substances that are covalently bonded do not dissolve into ions upon mixing with water. These can include polar molecules, they could include nonpolar molecules. So polar molecules that would dissolve but do not ionize are things like sugar. Antifreeze does not break up into any different ions, as well as alcohol. So in theory, sugar water does not conduct electricity, even though salt water will. So these substances, if they only break up into, or not break up, but they would result in 1 mole to 1 mole, if we were dissolved in water, they're going to have less of an impact on melting and boiling points compared to an ionic compound that dissolves in water. So they're still going to have an effect, although it's going to be a smaller effect compared to other ionic substances that would dissolve into more moles of dissolved ions. For example, sugar dissolves, so we have the solid designation that dissolves into aqueous. We start with 1 mole and we end up with 1 mole. So 1 mole of sucrose dissolves to form 1 mole of dissolved sucrose. No ions are formed, so this solution will not conduct electricity. So colligative properties are physical properties of a solution that are going to change and depend on the concentration of the solute in a given amount of solvent. Remember, the solute is what we are dissolving. It's always the smaller amount compared to 2 things in a mixture. And this is going to change our boiling point, and it's going to change our freezing point. And we use boiling point elevation because it's going to raise our boiling point, and it's also going to lower our freezing point. And this, in short, is why we add salt to water when you're making pasta. We'll explain that in a second. So the boiling point of water is going to increase as we add solute to it. The more solute that we dissolve, the higher the boiling point will go. And again, this is why we add salt to boiling water. It increases the temperature that the water boils, and therefore it cooks your food faster. So normally water at sea level is going to boil at 212 Fahrenheit or 100 degrees Celsius. The higher we go in elevation, the lower this number goes, but the more ionic compound, the more electrolytes that we dissolve into this, the higher this temperature is going to go. So if we were to add, let's say, a tablespoon of salt to our water to boil pasta, maybe it raises our boiling point up to 220 Fahrenheit. It doesn't seem like a lot, but the more salt that we add, the higher this temperature goes. And if you think about trying to cook your pasta in water that's, let's say, room temperature, 75 degrees Fahrenheit, pasta will cook in 75 degree Fahrenheit water, but it's going to take, that reaction is going to take a lot more time because of the lower temperature. So if we have a higher temperature, that reaction, remember, increasing temperature is generally going to cause the rate of reaction to increase. Higher temperature here will cause the pasta to cook faster. And that's why we add salt to it. A little bit of taste for that matter, but also mainly to raise the temperature to shorten the cooking time. Now the same thing is going to happen to the freezing point as we add solute to it, but it's going to go in the opposite direction. It's going to lower the freezing point. The more solute that we add, the lower the freezing point will go. And this is why we add salt to ice to melt it. We get the salt trucks on the road, putting salt down onto the ground. The salt mixes with the ice. It lowers the freezing temperature of that ice, and therefore turns it into a liquid. It essentially turns the ice or the snow that might have been on the road into salt water. And this only works to a certain point. If it's really cold outside, salt on the road doesn't matter. It's not going to lower the temperature low enough to cause it to melt. So this might lower our temperature from 0 Celsius down to, let's say, minus 10 degrees Celsius. So this is why we're adding salt on the roads in the wintertime. And in areas where the salt doesn't work or is ineffective because the temperature is so cold, oftentimes they just put sand on the road to give a little bit more traction, because at that point, salt's not going to do anything because the temperature is too cold. So when cars drive on the salted snow after the plows put it down, pressure and friction causes the snow to melt. Salt dissolves into that melted snow and prevents it from refreezing. The salt ions essentially get in the way of our water molecules from forming. And that's kind of backward. The H's should be the other way, but you get the idea here. These water molecules are trying to freeze, but there's these sodium and chloride ions in the way, and that's causing the freezing point to go lower. So the least expensive salt that's used is halite, sodium chloride. But in different areas, they use a different salts, such as calcium chloride. And we can get calcium chloride in the store around here, but it is significantly more expensive. And this is generally nice, round, clean looking white pellets. And this always looks dirty. But the CaCl2 is more expensive because it is more effective than the halite. Why? Well, sodium chloride is only going to break up into two ions, one sodium and one chloride ion. The calcium chloride breaks up into three ions, one calcium and two chloride ions. More ions that are dissociated is going to affect the freezing point and also the boiling point more. So the more ions that we can get in there to interact with the water molecules and interfere with them freezing, the lower the freezing point of the water will go. So I'm going to do a series of quick sample problems here just so you can see what you might be responsible for as far as answering questions involving colligative properties. And these are all just kind of worded in a little bit of a different way, but each of these we're looking at the concentration of the solute in the particular amount of solvent. And the more concentrated ones are going to affect our boiling point and freezing point more, and the least concentrated ones are going to affect them less. So of these four, which of the following solutions will boil at the highest temperature? Well, we want the one to have the highest temperature. We're going to want the one that is most concentrated. That's going to raise our temperature the highest. Now each of these have the same amount of solute, 100 grams, but varying amounts of water. So if we have the same amount of solute in a smaller amount of water, that's going to be most concentrated, and therefore it's going to have the greatest effect on our boiling point. So we have the mass of solute over the mass of solvent. That's our concentration that we learned in the prior lesson. Less solvent there is, the higher the concentration. So we can have less solvent or more solute. A couple different ways to look at that. So as the concentration of the solution increases, the boiling point increases. Which of these will boil at the lowest temperature? So for this, we're going to want the least concentrated. The least concentrated one will have a smaller effect on the boiling point. These are the same samples from prior, so the same amount of solute, 100 grams. So the least concentrated one will have 100 grams and the most amount of water, which would be A. So as the concentration of the solution decreases, the boiling point decreases as well. All the way down to the point where if we were to get rid of all 100 grams of sodium chloride, we would just have the regular boiling point of water. Which of the following solutions will freeze at the lowest temperature? So for each of these, feel free to pause the video and try these and check your work. So if they're freezing at the lowest temperature, this is freezing point depression, which means we're going to want the most concentrated. So most concentrated will lower the freezing point most or raise the boiling point. We're kind of extending, if we think of our line here, 100 Celsius, 0 Celsius. Freezing point depression is getting lower. Elevation is raising our boiling point higher. So the most concentrated would be D, and therefore would lower the freezing point the most. So as the concentration goes up, the freezing point is going to go down. Which of these will freeze at the highest temperature? I always think this is worded kind of weird. Highest temperature is going to be closest to the regular freezing point, so we're not going to depress our freezing point. We're going to keep it as close to the normal as possible, which means we're going to want the least concentrated solution, which in this case would be A. Lowest concentration have the least effect on our freezing or boiling point. So as the concentration goes down, the freezing point goes up. Just think of it as putting no solute into the water and just freezing the water by itself. Now, which of these solutions will boil at the highest temperature? So to boil at the highest temperature, we're going to want the most concentrated or more ions. So for each of these, we have 1 mole of each of these compounds, and they're in the same amount of water. So whichever one of these dissociates or breaks up into more ions is going to cause the boiling point to go higher. 1 mole of C6H12O6, this would be glucose. This would only break up into 1 mole. 1 mole of KBr, this is ionic. This would break up into 2 moles of ions. MgF2, ionic again, breaks up into 2 fluorides and 1 magnesium for 3 moles. And D, we have aluminum chloride, ionic, and that'll break up into 3 chloride and 1 aluminum ions for a total of 4 moles. So the one with more ions, D, will cause the boiling point to go highest because it's dissociating or breaking up into the most number of particles. The more particles that a solute ionizes or breaks up or dissociates into, the higher the boiling point will be. Now, as in chemistry, we deal with a lot of different trends, so you can see with a lot of these practice problems, the trends continue as well. So for this one, which one will boil at the lowest temperature? We're going to want the one with the least number of ions or the lowest concentration. We're going to look for, in this case, the least number of ions. Now, these are the same examples from before. We said this was 1 mole, 2 moles, 3 moles, and 4 moles. A would be the least concentrated, or would have the least number of ions, and therefore would have the least effect on the boiling point of the resulting solution. Fewer number of ions, smaller effect on the boiling point or freezing point. Which of these solutions will freeze at the lowest temperature? So we're going to want the most concentrated, the one with the most ions, which in this case would be D, because we're breaking up into 4 particles. So the more concentrated, the one with the more ions will lower our freezing point more and also raise our temperature more. So the more particles that a solute ionizes or dissociates into, the lower the freezing point will be. Which of these solutions will freeze at the highest temperature? So this is going to be one where we have the least effect on the resulting solution, or the one that is least concentrated, or the one that breaks up into a fewer number of particles, which would be choice A. It's only breaking up into 1 particle, which is the fewest amount of any of those choices there, and the fewer particles that a solute ionizes into, the higher the freezing point will be, or the least of an effect that the solute will have on that solution. If you guys have any questions, make sure you write them down and let me know. And good luck. May the colligative properties be with you. Have a great day.